Stephen Wolfram is here. He has been called one of the brightest minds of his generation. His first physics paper was published when he was only 15. 5 years later, at 20, he earned a Ph.D. from Caltech. In 1981, he became the youngest recipient of the MacArthur Genius Award. He went on to launch Mathematica, a software application that has set new standards for business and technology. Since 1992, he has been in self-imposed exile, working on this book that he believes will change the way we view the world. It is called A New Kind of Science, and it is easily the most talked about science book today. For all of these reasons, I am pleased to have him at this table for his very first television interview. Welcome. Thanks. It's good to see you. Since reading the story first in the New York Times, which was sort of grabbed my attention, and then there were lots of other stories about you, made me want to have you sit at this table and talk about this book. In your own words, as I said to you as we sat down, I want this simply to be a journey with you in exploration of your passion, your mission, what it is that you have learned, and the nature of your own personality that drives you forward. Having said this, tell me in your words the importance of this book, A New Kind of Science.
Well, this is sort of the outgrowth of about 20 years of work that I've done. Kind of started in the late 70s. I was working in various problems in physics and so on. And one of the things that happened was several kinds of problems I was looking at, they all seemed to get stuck in the same way. There were questions that I was asking, usually about how sort of complicated phenomena that we see in the universe work, that I wasn't able to make progress with all the fancy tools that I'd learnt from doing theoretical physics and so on. So I kind of got to thinking, there must be something different, there must be something more, something that one's been missing in the usual tools that are used for things like theoretical physics.
Yeah, fair to say you were looking for a big idea, or that these tools would lead you to a big idea?
At the time, I wasn't sure how big the idea would be.
Okay.
At the time, all I knew was there's something missing, there's something, I'm getting blocked somehow.
Fair to say that it was mathematical equations were not taking you where you wanted to go.
Yes, mathematical equations are sort of the proudest achievement of the traditional approach to theoretical science. And they've been sort of the mainstay of what's been done in the exact sciences for 300 or so years. And I believed, as most people have, that this would be the way to make progress on things.
So you went out to do your garden, and you didn't have a rake or a hoe, and you needed to find one to figure out what was in your garden.
Yes, so I got interested in what could one do if one wanted to go sort of beyond mathematical equations, and what else might there be out there. And one kind of realizes if one wants to do theoretical science, one has to believe that the universe, that nature follows some kind of definite rules. The issue is, what are those rules made from? Are those made from the kind of constructs that people have put into mathematics, or might there be something more general, something beyond mathematics, that the universe might be using to figure out what it's going to do? And so what I started realizing was there are more general things than what's in mathematics and calculus and numbers and equations and these sorts of things. And what one realizes is that computer programs, the kinds of things that we put into computer programs, give us a sort of concrete way to think about more general kinds of rules. So what I got interested in the early 1980s was sort of what else is out there if one looks at more general kinds of rules than the ones that have been used in mathematics. What is there that the universe might be using? And sort of the thing that I got started on was kind of the question of, if you look at programs, computer programs, what do typical computer programs do? I mean, the kinds of programs that we're used to running on computers are ones that we've specially built to do the particular things we want to do, whether it's word processing, computing some mathematical thing, those sorts of things. But if one just says sort of in the abstract, what does a sort of an arbitrary computer program do? That was a question that hadn't been addressed, and that was a question that I thought was important to look at, because I thought that might be what the universe was doing. And so what I kind of started on was an exciting thing for me, because it was sort of, it's like, I suppose, when people first had microscopes, they could, take a piece of pond water and look at the pond water under the microscope, and they saw all these little creatures running around.
Yeah, exactly.
And so what ended up happening was I started using computers to do experiments on sort of what are the creatures out there in the computational world? What do these simple programs typically do? And what I found was things that I never would have guessed, things that were extremely surprising and what sort of started me on the journey which has eventually led to making this book of mine.
10 years in the making,
Yes.
working on it almost every night.
Yes,
Yeah.
indeed.
How big an idea do you think this is? that's incorporated in this book?
I think it's important. I think it's the kind of thing that will change greatly the direction that science and technology go in.
How so?
Well, so one of the questions is sort of what do you base science on? You know, where do you go to find models, to find things that might represent the way the world works and so on? And sort of the traditional view has been you go to mathematics to do that. What I'm saying is that if you go to the sort of computational world of simple programs and so on, there's a much richer vein to look at.
Just to stop you only because I suspect I'm where the audience is. I want to understand, and it's important, and at the same time, I'd rather go slow rather than fast and suggest that I didn't understand or understood. You are saying that what you found is that if you wanted to explain the way the world works, what created order, what created other things, you needed to look at programs, like computer programs, to explain it.
Yeah, let me show you. I have an example. One of the big questions is sort of, if you have a very simple program, what might it do?
Right.
You might think if the program is really simple, it's always going to do something very simple. Here's an example of how this works. This is a program, it's called a cellular automaton.
Right.
And you have a line of cells that are either black or white.
Right.
And then in successive steps, it just evolves down the page.
Right.
There's a very simple rule here that says what color a particular cell should be based on the color of cells on the step before.
Right.
You start off with one black cell. In this case, you get just a very simple, uniform black pattern. Okay, so it was a simple program. You started it from something simple. It made something simple.
Right.
This is kind of what we would intuitively expect. This is what I would have expected before I started doing the computer experiments I did.
Right.
So then the question is that always how it works, or can other things happen? So this is another example. Here's just another one of these programs. We started off from one black cell up here, and then we let it run for a while, and this is what we get. This is something much more complicated.
Yeah.
Still, you can see some regularity. This ends up being one of these so-called fractal or nested patterns in the end. But this is, again, something which where we can already see that even though the rule is very simple, the pattern we get is slightly more complicated. Okay. The thing that was really sort of the thing that really made me realize that there was something more going on that I didn't understand was something that I first saw in the middle of 1984. And it's this picture. This is a thing that in the scheme for specifying these programs is called Rule 30. And the way this works, this is the rule. This is the whole program up here.
Right.
You started off from one black square here, and then this is what you get. And what's remarkable about this is, even though it looks like you sort of didn't put anything in, you just have a very simple program, you put in one black cell, you get out this complicated thing here.
Right.
And this is something, this sort of violates our normal intuition, because normally when we think about sort of building things in everyday life, in engineering and so on, if we want to make something complicated, we expect that we need to go to a lot of effort to make that complicated thing. But this is a case where that's not happening. We have a simple rule, we have a simple initial condition, and yet we get something complicated. And it seems sort of, it effortlessly produces something complicated. What's, I think, particularly interesting about this is when we look in nature, we also see lots of complicated stuff that's been made seemingly effortlessly by nature. And so the thing that kind of really got me excited about this was the idea that perhaps whatever is going on here is also the essence of what's going on in nature and the way that nature makes complicated stuff. And that sort of, it was this sort of discovery that really got me started in the direction that's eventually led to all the science that I've done.
And this is called cellular automata?
Yes, this is the Rule 30 cellular automaton.
Okay. Now, you later began to look at patterns in shells and explain to me the significance of that.
So one of the questions is, there's the issue of when we see complicated things in biology, or in nature in general, how is nature making that complicated stuff? Does it have very complicated rules that it's applying as we might expect if we were going to make a pattern as complicated as that by some engineering process? Or does it have some very simple rule that for some abstract reason inevitably makes something complicated? What you find, well, for example, here's an example of a shell.
Yeah. Oh, wow. Yeah.
Where you can see the pattern on it is quite strikingly similar to some of these kinds of patterns made from the computer. And one might have thought when one saw a complicated pattern like this that the shell must have had some very complicated way to make this, the mollusk must have had some very complicated way to make this, or perhaps that some elaborate process of evolution had sort of carefully controlled it to make this kind of thing. But what the things that I found suggest is that, in fact, you can just have a very simple rule that might be sort of picked randomly in the space of possible genetic programs, and that sort of inevitably, even that simple rule can produce this complicated stuff.
What idea are you, I'm asking you to repeat yourself, are you getting from this?
Well, I think one of
other than simplicity.
Right. So one of the issues in biology, for example, is could there be a theory of biology?
Right.
Okay, from the sort of Darwinian tradition, one has the notion that what we see today is the result of a long series of historical accidents in evolution. The fact that it's this shell rather than some other shell was a consequence of some accident that happened to some mollusk in the Cretaceous period or some such other thing. Okay, and one sort of imagines that there can't be a theory in biology. But one of the things that's come out of what I've looked at is that, in fact, that might not be the case, that it might be true that sort of what's happening in biology is that biology is sampling a large collection of possible simple programs, and that it's sort of an inevitable consequence of it using simple programs that certain forms, behavior occur in biological systems. And so there's the potential from that of saying we can, to some extent, predict what we might see in biology, rather than just having to sort of wait and look at the historical and sort of imagine that it's something that's a consequence of historical accidents that we'll never be able to kind of address in a scientific way.
Today, after finishing this book, what's the biggest question for you?
Well, there are many sort of in many different directions. This book has opened things up. So, for example, in physics, one of the things that I've been interested for a long time in sort of fundamental physics and what kind of underlying theory there might be for the universe. One has imagined, by looking at sort of the history of progress in that question in physics, that if there is an underlying theory of the universe, it must be something very, very complicated. Because it seems like every time you kind of peel down to a smaller scale in physics, the equations get more complicated, everything gets more complicated. From the things I've seen, I kind of got the hope that perhaps it might not be that way, that instead there might be some very, very simple underlying rule that produces all the complexity and richness that we see in our universe. So one of the things that I tried to do in the book was to try and see what might that rule really be like. And one of the things one realizes
that explains the universe.
That explains the universe. So what I'm interested in there is, could there be some simple program, some simple set of rules that if you run it for long enough will reproduce in precise detail everything that we see in our universe. And if I hadn't observed the things that I observed from the computer experiments that I've done and things like that, I would never imagine that that could even conceivably be possible.
And now you believe... Go ahead.
I'm very convinced that not only is it possible, but that it's almost certainly true. And that one day, perhaps even soon, there'll be a time when we'll be able to say, this simple set of rules, this is our universe. And there's a question of sort of what might those rules be like? And what kinds of things, how familiar or not might they seem? So even things like space and time, which seem to us now sort of intuitive concepts, you have to kind of break them down into something smaller if you're really going to pack our whole universe into a small rule.
Go ahead.
So for example, in the case of space, we sort of imagine space as being kind of this continuous thing where you can move through it continuously. In kind of the way that I imagine things might be, space is instead much more like at a very small scale, like a kind of network where you just have these points that are connected in a certain way, and kind of at the lowest level, there isn't anything that sort of looks like space as we know it. It's kind of like in water or something.
Yeah. No, go ahead. I'm sorry.
It seems like kind of a continuous fluid when you just look at water in a glass. But if you look at what's underneath, it's a bunch of discrete molecules bouncing around. And so similarly, I suspect that in the case of space, there's something a bit like that going on.
Let me try to make an analogy and tell me whether it means anything, even as a question and with respect. The people that map the human genome have said to me, and all of them that were involved in this, all of the leaders, have said to me, to a person, while genes are destiny, it only explains 50% of it. 50% of it is environmental. What's the equivalency of that idea in terms of what you are talking about, in terms of a certain set of rules? Is it chance? Is it accident? Is it something else?
Well, so one of the features of the kinds of rules I'm talking about is that once you've set up the rule, what will happen is always the same. There's no chance to kind of get sort of environmental effects coming in from the outside. But one of the things that's interesting is you might have thought once you know the rule, you know everything about what's going to happen. And but the sort of the big thing that comes out of what I found is that that's very, very far from being correct.
Now, why?
Well, okay, very good question. I spent a long time trying to figure that out, and I think I now know the answer.
All right.
So the issue, it's a little bit of a long story, but the question is, given the rule, you produce some behavior.
Right.
Now, there's an issue of kind of, can you foresee what that behavior will be from the rule itself? Now, if you could foresee it, what it means is that you, with your brain, with your mathematical computational methods or whatever, can in a sense shortcut what the system itself is going to do. So let's say the system itself is going to run for 1 million steps. If you could foresee what was going to happen in it, what that means is that you, with sort of less effort than those 1 million steps, could say, the system, it may take the system a lot of effort to find out what's going to happen, but I can know that after 1 million steps, the result is going to be this. And that's, in a sense, most of traditional exact science is based on the idea that one's able to do that. So, for example, a typical thing is when you look at, let's say, the idealized model of the Earth going around the sun. Right. You get some mathematical formula which says where the Earth is going to be at any time. And what you can then do is, if you want to know where's the Earth going to be 1 million years from now, you can just plug some numbers into that formula and immediately answer that question. You don't have to trace 1 million orbits of the Earth around the sun to find out what's going to happen. But in a sense, what that assumes implicitly is that you, as a predictor, as an observer, are somehow computationally more sophisticated than the system itself. While the system itself had to go through its 1 million steps or some such other thing, you, as a predictor of the system, were sort of able to be smarter than it and to figure out what it's going to do without going through all the effort that it had to go through. This is an idea that I call computational reducibility.
All right.
So now so here comes the crucial point.
All right.
The issue is, how do we, our brains, our computers, things like that, how do they compare in their computational sophistication to these simple programs and things like that? And the crucial thing is this thing that I call the principle of computational equivalence, which is the idea that, in fact, these systems are equivalent in their computational sophistication to us as observers. So what that means is there's sort of a competition between the system itself doing its thing and us trying to predict what it's going to do. And we might have imagined that we were always sort of so computationally superior to these systems that we could work out what they were going to do much more easily than they do it themselves. But this principle of computational equivalence implies that that isn't the case, that instead that there's a computational irreducibility to the behavior that one sees, which means that if it takes, let's say, 1 million steps for the system to do such and such a thing, we're not going to be able to work out what it's going to do by any procedure that's much more efficient than essentially just running it for 1 million steps. So what does that mean in the case of something like biology?
Right.
What that kind of means is that if you have given the genetic program, you might say, okay, once we have the program, we've solved the problem. Because once we have the program, we know everything about what's going to happen, let's say. What this is saying is that even given the program, it can still be hard to tell what's going to happen. Even given the program, knowing whether this particular program is going to lead to an organism that only grows for a while and then stops, or to an organism which keeps on growing forever, or something like that. To answer questions like that may be sort of irreducibly difficult. And the only way to do it, in a sense, may be to just sort of run the program and see what happens.
10 years, big ideas, tools, models. How have your fellow scientists accepted the ideas incorporated here?
Well, this book has only been out and about in the world for 3 months.
Yeah, 3 months, right, July, right.
So it came out May 14th.
May 14th, right.
I'll know that date forever.
Right. I first heard about it in July, right.
I would say that it's interesting. I mean, science is used to making progress in small steps. I mean, it is the common pattern of scientific progress is that there's a large number of scientists, and most of what happens is sort of small incremental progress. What I have tried to do is to kind of take a bolder step. That's something very unusual in science. And many of the aspects of many of the things that I've had to do in order to take a bolder step are things that are quite unfamiliar to scientists. For example, it wouldn't have been useful for me to write my book sort of aimed at some level of technical specialists, because there aren't any technical specialists in the things that I'm talking about, at least not yet. So it's sort of something which is kind of a little bit of a shock to the system. However, I would say that the response certainly of what one might call the high end of the scientific community has been very positive. I mean, in the sense that there's been people who view themselves as sort of doing things that might have been a little bit similar to some of the things that I might have been doing are less likely to have read the book at this point than people who are further afield.
Why is that?
I think it's a feature of kind of people who are sort of closer figure. They must know everything that's in the book.
I look at this shell and I see a pattern. It reminds me of a zebra pattern. Now, wasn't it someone touring who would explain that to me? Okay, so the
question of sort of how you make patterns like this, this particular one is one that there have been models for patterns like this for a while. Alan Turing was one of the first people to come up with them. Interestingly, I mean, sort of one of the issues is kind of, when you try to make a model of something, one of the questions is sort of how much do you get out for what you put in? And what becomes most interesting is when the model is very small, but what you get out is very big. I think what happened, for example, with Alan Turing was actually quite interesting. Alan Turing was most famous for having come up with the idea of universal computers and Turing machines and so on. Towards the end of his life, about 20 years after he did his work on Turing machines, he got interested in theoretical biology. And he kind of asked the question, how do certain kinds of patterns arise in certain kinds of places in biology? And strangely, he didn't look to Turing machines as sort of the thing to be sort of the underlying stuff that one might use to make such models. Instead, he said, well, I know this. It's like physics. It's like differential equations, which are kind of the mainstream thing in physics. And he sort of said, I have to use differential equations to do this.
So he took the wrong step. If he'd looked at universal computing, he would have been on the right direction.
I think so. Yes, I think so.
And he did that when?
1954 was
now,
when he
did
died.
that give you any insight as you were looking at what you thought where he made a misstep and went in the wrong direction? Was that along your 10-year journey instructive?
Well, I tried very hard to study the history of a lot of the things I was doing, because I found that one of the things is, as I looked at different areas of science, often the things that I discovered seemed to be at variance with sort of conventional wisdom in those areas. And so it's kind of a scary thing if you've long
You're
believed...
running in the face of conventional wisdom.
Yes, I mean, in many different areas, in physics and biology and mathematics and so on, the things I discovered seemed to be against what conventional wisdom would say. And so that when I had long believed that conventional wisdom, there was a question of sort of how could I get confident that what I now believed might make some sense. And sort of the best way I found to be able to figure that out was to go back and look at the history of these fields and to sort of ask myself, why did they take the step that they took?
I understand, yeah. And then Turing is an example of that. So what is the biggest idea that was part of our conventional wisdom that you believe your ideas discredit?
Well, so I think one has to break that into different areas. I mean, one of them...
Just give me one, but go ahead. Answer it the best way you can.
I think sort of the idea
take
that
Darwin,
mathematics...
for example.
Well, I was going to take a different example to start
Go
with,
ahead.
Which is sort of the idea that mathematics is the sort of key to the sciences. That's been an idea that's been around for, well, it became big 300 years ago or so. I think that idea it is certainly true that great successes can be achieved by using mathematics in science, but there's more that hasn't been found that I think can be found with the kinds of things that I've tried to introduce. you mentioned Darwin.
Right.
One of the issues there is sort of when you see complexity in biology, where does it come from? That is, when we see all these remarkable things, whether it's pigmentation patterns, whether it's other kinds of forms, sort of what's the fundamental origin?
Go ahead, and you say?
Well, what has been said, and it's been a kind of a mystery. I mean, it's one of the reasons that I think Darwinian evolution has always had many people questioning it, because it's it doesn't really explain that. And what I'm saying is that it's actually easy to get this complexity. It's easy to get things that are complicated.
The word that keeps coming back in what you have done is your own. You make a prodigious effort, and you come to simplicity.
Yes.
Fair enough.
I mean, I think that in a sense, what what I've tried to do is to find out, is there something simple that underlies all this stuff that seems to us complicated when we first look at it, and it's often turned out to be the case that I found a lot more simplicity than I ever expected to find.
A programming concept. Here, do you believe, and then we're way off, I realize this, we're also way over, is there a big idea that connects what you talked about in terms of a theory of the universe, a concept, an idea about the way the universe works, with an idea of the way that biology works, with an idea that way other phenomenon. Is there one idea that ties all of those pattern-generating things together?
Yes. I mean, this is one of the big outgrowths of what I've tried to do.
That's the big one, isn't it?
Which is sort of how, I mean, this idea of thinking about all these different processes in nature as being computations of some kind, and then kind of comparing those computations, and that's where this principle of computational equivalence thing comes in.
Stephen Wolfram, A New Kind of Science. Thank you. I hope you'll come back. It sounds awfully complicated. On the other hand, it is part of the ideas that people talk about, trying to understand the way things work. In the end, that is his pursuit, I think. Thank you.
Thank you.